So now that we have correctly formatted our CSV files for use in GuPPY, let's go ahead and put our Plexon multi-wavelength for our photometry data through this program. To start up GuPPY, there are 3 lines of code you need to use after you initially install it. And so this is actually really well documented on the GitHub page for GuPPY. They have a very nice wiki where you can look at all these instructions. And this will open a graphical user interface. The first thing to do, of course, is tell it where to locate your data files. So I find it's easiest if you have the data files on your user folder, the C drive, because that's where it defaults to. And then you have to select the folder, go down into the folder until you have just the folder that has all your data files into it. And then you want to use that folder, not the individual data files within it. You want to move over the entire folder. And that just makes everything a lot easier, and then you can add multiple different folders. The next is to set all your parameters. And so you do have to set all your parameters prior to running anything. So over here on the left, this column is what I'm going to call your general parameters. It's, do you want to use an isosbestic control? Do you want to combine data across your data files? How much time do you want to eliminate at the beginning of your file? So here it's asking seconds. pMAT it asks for samples. So I'm rounding up to 58 seconds. Here is a window for moving average filter. GuPPY says for the slower collection rate of 20 to 30 hertz seen in neurophotometrics and Plexon systems, you want to set this anywhere between 5 and 10, whereas for TTT data, it should be around 100. Again, this is just because of a difference in collection rates. Let's see, so then this is asking what type of graphs we want to see for these different analyses. So for peri-event histograms, for transients, and for just a plot. So I'm just going to put z-score for everything. And then this moving window for transient detection in seconds, I just put a second here. And that seems to work for these data. So I'm not working with any group analysis, and I'm not really changing the visualization parameters, but these are things that you could play with if you need them. Okay. So I didn't explain in the pMAT about the area under the curve analysis, which is part of the package, because you don't have to select or set any of those parameters to run any of the other analyses. Here, if you're not using area under the curve, make sure you set these to 0. Okay. So then at the very top, we have z-score parameters. I'm just using a standard z-score, but there are a couple other options. Again, everything is explained in their wiki on the GitHub page. So here are my peri-event histogram parameters. So I'm going to set these as close as I can to the same parameters I used in pMAT. This time interval was actually a little tricky for me to understand. So it explains it up here, but let me see if I can explain it in different words. So this time interval is to prevent overlapping timestamps or overlapping peri-event histograms. So if you have TTL pulses that you know should occur at least, say, 2 seconds apart. So every behavioral event or every TTL pulse or every tone should occur at least 2 seconds apart. If you have a TTL pulse that occurs at a half second or 1 second after some initial TTL pulse, then you know those ones in between the initial one and the one that happens 2 seconds later are spurious. You don't want those. So this time interval, you can actually remove those extra or super fast or not needed or aberrant timestamps between what you know should be actual timestamps by setting this time interval. I want to count every single TTL pulse, so I set this time interval to 0. So baseline parameters, just 1 second to 0. And that's everything I'm going to set here. Everything looks good. So I'm going to save all these parameters to a file. Then I'm going to open store names. So store names will open a separate user interface, and this is where you can select which files you want to use. And then there's also instructions if you want to use one of these files, say your control 410, as the control for multiple files. So if I had a 560 nanometer data in here, then I could use that 410 control for both the 465 and the 560. However, we're just doing simply here, just using these 3 files. Store names, based on my experience and some of the errors posted on the GitHub page, are kind of difficult. So store names trip people up. So there are instructions over here, and these are absolute naming instructions. They don't sound like it from the way it's worded, but they are absolute. So the isosbestic has to have control underscore in its name, and the signal has to have signal underscore in its store name. And then the region, that's either region, description, whatever, and that region has to match between the control and the signal. So let me show you what I mean. So I've selected my files, I hit select store names, nothing seems to happen, and that's because an extra window popped up over here. This is something to be careful of in GuPPY. It opens lots of windows and doesn't necessarily bring them to the foreground. So here I don't have any actual store names. If I go through and run this analysis again, it will remember the store names that I had for particular files. So right now I'm just going to hit show and then close it. You have to close that window to continue. Then I have a little bit of code that appears here. Right here, it filled in these green areas. These are my file names. If you scroll over to the right, it has names for store names. So I'm going to hit enter. You can hit enter in this so that's on the next line so that you can read it. And then I have these blank spaces. This is where you want to put in those store names. And they have to match in order your file names here. So my first file was for 410 data, so that's my isosbestic control. So I'm going to say control underscore F1. I'm using F1 for fiber 1, but you could also put the region here. So control orbitofrontal cortex, control amygdala, essentially. The next file is my 465, so signal underscore F1. So there my region or my description matches. And so I have a control and a signal for both. And this is necessary because I have said look for an isosbestic control, and that was in my original settings under the GUI. So then finally the last file is my behavioral TTL pulses. The naming for this is less strict, and you can just name it whatever your event was. Here it's airpuff. So then you either overwrite or create a new one and then hit save. And this says it is correctly saved. Now I can go back to my original GUI. So those store names are difficult to get right, and so you might encounter a lot of errors there. And where you look for errors is actually in the Anaconda prompt. And the reason I mention this is because I ran into a couple different errors. I ran into a chunk data error, I ran into various store name errors, and with one file I ran into a very peculiar column number or row number error, which I couldn't determine the root cause of, but I believe was specific to a particular file. And the reason I'm going into this and the fact that I ran into multiple errors is you can read more about them in the written part of this post. But just be aware that errors will occur and they will show up in the Anaconda prompt. Okay, so now I'm going to hit read raw data. I'm going to pull up that Anaconda prompt again to show that it's actually doing things. Raw data fetched and saved, good to go. extract timestamps. You know it worked because it popped up with figures. Okay, so here are just examples of my figures. So pMAT will automatically save these. So if we go back to here's our session 11 folder, and we go into our GuPPY data folder. And then we have told it to look at the session 11 data. Here is an input parameters. This is a new folder that GuPPY created. This is where your session parameters are saved. So if we go into the data folder, we can actually now see that there's an output 1 folder. And so this output folder is where your figures and your HDF files will be saved. Notice that these figures here that popped up did not save automatically. You do have to save these figures manually if you want them. But we're just going to go ahead and close them for now and continue on. So we're going to do the pair event histogram computation. I have my anaconda prompt here, just seeing if there's going to be any errors. Okay, and so we know it's successful because it came up with this transient or peak analysis image. So again, you have to save this figure manually if you want, but the associated data is saved in your folder already. So close that, and then we can open our visualization user interface. So this is actually a really nice feature of GuPPY because it gives you a little bit of extra flexibility in looking at your figures and modifying them. So here are line graphs of the average of your behavioral data. So I just have my air puff here, but if you had multiple events, you could select your events. So then I can actually change my x-axis a little bit, make it more appropriate for my data. This looks like a pretty good y-axis, so I don't need to change that. I can change my plot height, plot width, and then of course I can save. And then I can save the individual figures as well. There's also up at the top a tab for the heat map. So this is a really big heat map when it first pops up. So I make it a little bit smaller. Maybe that's a little bit too small. You can edit. The point is you can edit it, so to make it the size that you want it. You can also save it as different file formats. You can change the color map, which is nice. There is a lot of different color maps. This is just the default. Again, if you had different events, you could do multiple events, and you can save this. So all these data are saved back into this folder. So most of them are saved as HDF5 file formats or H5 file formats, but there are some CSV files. And then if you want to save your data, you can just click, or your figures, you can click on this little save on the right, and it will download it for you. So I'm not showing some of the more powerful features of GuPPY, like the batch analysis, the group analysis, or the artifacts tool. I recommend GuPPY if you have more complex data sets that would benefit from the use of these tools. So be patient as you navigate through the learning curve. I described a couple of the errors I ran into. You're likely to run into a couple errors as well because GuPPY requires very, very specific formatting for your inputs. However, it is well worth it to be able to use these more powerful tools. So I hope you found this series on using open source tools, pMAT and GuPPY, for analyzing multi-wavelength fiber photometry data collected on a Plexon system. As always, if you have any questions, please contact us at support@plexon.com.